This on record, minimize it, and then take a snapshot. I assume you just want to start at 1?
Yes, perfect.
Okay. The way we're going to do this is we're going to draw vertical rectangles. To find the area of the shaded region. Now, what does that amount to? If I was finding just the area under the red curve, I would take the integral of 9x minus x squared, right? Mm-hmm. From 0 to 7. But that would give me all of this area. And I don't want the triangular part. So I would also subtract out the area of the triangular part, which is also the integral of that function, which is 2x from 0 to 7. So that's essentially what you're doing when you find the area between two curves. And it's generally written as f of x minus g of x. But what it really is the upper curve minus the lower curve. Always has to be that way. Okay. If they switch places, in other words, let's say they wanted us to find the area all the way over to 9. Well, notice that after 7, the blue line is above the red line. Mm-hmm. So I wouldn't be able to do it all in one step. I'd have to go from 0 to 7, where I'm going to take the red minus the blue, and then I'd have to go from 7 to 9, and I would take the blue minus the red. So it's always the above function minus the below function. So if we do that, hold on, I'll get there, I just haven't mastered this eraser yet. Okay. In other words, the best way to do this is not with two integrals. The best way to do it is by combining the two functions. In other words, take 9x minus 2x. And so what we're really going to integrate is 7x minus x squared dx from 0 to 7. And that's going to give us our final answer. Okay? So help me integrate this. We need an answer that you can put in that square. So first of all, let's find the antiderivative, and then we'll evaluate it from 0 to 7.
Okay, so the antiderivative would be 7 over 2x, oh wait, yeah, x squared, right? 7 over 2x squared minus...
I don't want to mess with your process if that's the way you've learned how to do it. But I'll be quite honest with you. I always start with the exponent, whether I'm differentiating or integrating. My first step is to add 1 to that exponent. Now, I go ahead and write the 7 because I'm not really doing anything to the 7. But the next thing I'm going to do is add 1 to that exponent, and then I'm going to divide by the new exponent. That's how I apply the power rule, in that order. And if you always do it in that order, you'll never get messed up. What's the next part?
Okay, so the next part is x cubed over 3, yep. Or so 1/3.
Yep, no, just like that. That's fine. Okay. And now we're going to evaluate that from 0 to 7. And so how do I do that? I'm going to start writing over here on the left. Okay. Because I'm out of room.
So you take, isn't it 7?
Start at the top. not the bottom one, the top one. So it's 7 times 7 squared over 2 minus 7 cubed over 3 minus the value of that function evaluated at 0, but we can see that that's 0.
Yeah.
You understand?
Mm-hmm.
In other words, we've got two sets of subtraction going on here. We got the first one where we subtract this from this. Whoops. First one where we subtract this from this, and then we got the second one where we subtract the whole thing evaluated at x equals 0, the bottom limit of integration. And we can see that that's 0, so we don't really have anything to do for that part there. But we do have to figure this one out. Let's see, 7 cubed is
343.
343 divided by 2 minus 343 divided by 3. Now, the question is, how are we supposed to put that in?
Let's see.
You can convert it to decimal.
Yeah, I think I could do fraction, decimal, whatever way I want to.
Okay. Shall we go on?
Yes.
Okay. Yeah, I don't want to waste your time figuring out how to come up with that number.
Yeah.
Especially when I don't know whether we're supposed to put it in as a... In other words, you could convert everything to sixths, common denominator of 6, and then put it in sixths. And that's going to be the most accurate. The problem with putting it in as a decimal is then you might have to end up approximating it by rounding it off. So, I don't know. All right, let's go to the next one. Now notice this is different. What's different about it is that this blue thing isn't even a function. And it's x equal y squared minus 2. It's not y is a function of x, it's x is a function of y. And that is a parabola, and if you remember from your conic sections, that's a horizontal parabola, and that's what we're looking at. And the red function is also a function of y. In other words, it's x equals some function of y. And if we look at the shaded area that they want to figure out, notice that there'd be problems if we tried to do this. If we tried to break it up into vertical rectangles, we got big problems because we're not able to define these points as well. It's hard to explain why it's difficult to break it up vertically. But once I show you that we're going to break it up horizontally, you'll get it right away as to why it's better. Notice the height of each of these rectangles is one function minus the other function. And we're going to integrate it along the y-axis, not the x-axis. So we're going to, and we always take the function on the right minus the function on the left, just like we always take the function, the upper function minus the lower function when we're integrating along the x-axis. But this is going to be this red function, which is e to the y, minus the blue function, which is, parentheses, very important here, y squared minus 2. In fact, I'm going to put parentheses around both just to clarify that that's the red minus the blue. and it's dy. It's not dx. In other words, this differential over here, when you're integrating, is always the same as the variable in the function. They can't be different. If this is an x and that's a dy, I'm stuck. I can't do it. Now, what are my limits of integration?
Is it 1 and -1?
Always go from bottom to top. So it goes from -1
Oh, okay.
to 1. In other words, this point here to this point right there.
Okay.
And like I said, I'm going to integrate along the y-axis, and then I'm going to sum up each of those rectangles to get my answer. And that's basically what this integral sign means, is I'm summing up all of these functions, but I'm doing this along the y-axis. So now let's integrate that. And again, it's straightforward. First of all, let's remove the parentheses. I'm going to go up here on the left where I have a little more room. I'm going to move the parentheses. When I remove the second parentheses, what do I get?
Oh, wait, you take the antiderivative, so it's going to...
First of all, let's just remove the parentheses.
Okay, so then is it just y squared plus 2?
It's minus y squared plus 2. In other words, this negative sign has to be distributed to both the y squared and the minus 2. And it turns it into a plus. So that's why the second set of parentheses is vitally important. Otherwise, you'd end up with a minus 2 and we'd get the wrong answer. Now, we're going to go from -1 to 1. Let's find the antiderivative of that. And now, I can actually add another set of parentheses and put dy there, like that. But I'm still going to integrate it term by term. In other words, integration is really easy if you're just adding or subtracting a bunch of terms. It only gets really hard when you start multiplying or dividing a bunch of terms. Then integration becomes a bear. But as long as it's one term at a time and I know how to find the antiderivative of each of these three terms, what is it? What's the antiderivative of e to the y?
Is it e to the y squared over y?
No. That would be applying the power rule. But you can't apply the power rule when your variable is in the exponent. In other words, remember what the derivative of e to the x is? E to the x.
Oh.
So the integral of e to the x is e to the x. Or in this case, the integral of e to the y is e to the y.
Okay.
Now we can apply the power rule to the other two terms. What's the next term?
Minus y cubed over 3.
Yeah, and that's the very first thing I did was just add 1 to the 2. If there would have been a coefficient, I would have written it in there and simplified afterwards. Don't try to simplify that coefficient and the new denominator in one step. That's an excellent way to just make a mistake. What's the integral of 2?
Is it 2y?
I'm evaluating this whole thing from -1 to 1. Sometimes when you go from -1 to 1, it's a symmetrical figure, and you can go from 0 to 1 and double it. This is not one of those times. You'll notice that the area above the x-axis is bigger than the area in blue below the x-axis. So there's no symmetry here. So I have to evaluate all of it at both numbers. So tell me what the next step is.
So it's e to the 1. Then
I would just plug it in and then simplify. Don't try to simplify first. Just plug it directly in. In other words, like this, 1 cubed.
Okay.
If you end up trying to solve it at the same time, that's another great way to make mistakes. Okay? So I'm going to put all of that in parentheses. And then I'm going to subtract from that everything evaluated at -1. So e to the -1 minus a -1 cubed. Oops, I forgot the 3 underneath, didn't I? There's the 3. Here's the 3 here. And finally, plus 2 times -1. Now you can kind of see why I said just substitute first. Look at how many minus signs we got. We got 1, 2, 3, 4, 5 minus signs, plus another one in the exponent. It is so easy to make a mistake here, it's unbelievable. So you have to be really, really careful. And that's why it's best to just substitute in and then go back and solve. Okay? So now let's simplify. That's e minus 1/3 plus 2 minus, well, that's 1 over e. What's this? That is -1 cubed, which is -1. A minus times a minus, that's plus 1/3 minus 2. And again, these parentheses are vital because the subtraction sign in the middle's got to be distributed to everything. So what's this end up being? Let's see. We got e minus 1 over e. I'll start there. I got minus 1/3 minus another third. That's minus 2/3. And I got plus 2 plus another 2, plus 4. There's our answer, pretty much. Again, a calculator will put a number on that. So let's not worry about doing it. In other words, once we get it to this step, I'll turn it over to you.
Okay.
But up to that step, you can see that there are 100 ways to make a mistake, even when you're dealing with numbers like 1 and -1. So I would say the best absolute way to do it is exactly how I've done here, one step at a time.
Okay.
Similar type situation in that we don't appear to have functions of x. The blue or the red do not pass the vertical line test. So they must be functions of y. And they are. If we look at them, we got x equal y squared minus 8y, and we got x equal 5y minus y squared. So again, this is just going to be subtraction. So set up the integral for me. This time I'm going to try to work left to right, so you don't confuse.
So it's y squared, parentheses, y squared minus 8y.
Hold on. Got to start with the one on the right. I'm not sure I can tell by the way they've labeled this. Can you?
No.
I'm assuming that this x equal 5y is the blue.
Oh, yeah, yeah.
It doesn't make sense that they would make that the red. Right? If you got to pick one equation for each color, I'm going to call this upper one the red.
Yeah.
Which means I've got to take this minus the upper one.
Oh, okay.
Remember, you take the one on the right minus the one on the left when you're integrating along the y-axis.
Okay.
So it's going to be 5y minus y squared, that's the blue, minus, and again here the parentheses are vital. If I don't use parentheses, I'm going to get it wrong. Only because subtraction is going on. And I do have to take this function and subtract that whole function. And then it's dy. What are my limits of integration going to be?
0, 5.
Well, remember I'm going to integrate along the y-axis. So what's that y value right there? That's my upper limit of integration.
Oh, 5. Like 6.5, I guess. Oh.
Give it to you right there, 13 halves.
Okay.
We'll just write it as 13 halves. I like improper fraction a lot better than proper fractions. Makes more, they're easier to deal with, actually. Proper fractions end up always, you need to convert them to improper fractions to really work with them. Okay, now remove the parentheses. That becomes a plus 8, excuse me, right? That's the only thing that changes when I remove that second set of parentheses. Now simplify the expression, starting with the y squareds.
So that is negative 2y squared.
Okay. How about the y's?
And then 5 plus 8 is 13y.
Plus 13y, and that's it. And then we're going to put dy. And whenever you have a final function that's complicated, you put it in parentheses, just because they usually do. In other words, the dy is not applying to just the 13y. It's going to apply to that whole function. And we're going from 0 to 13 halves. So let's find the antiderivative.
So that is negative 2y cubed over 3.
Good. That's the way I like to see you do it. Yeah.
Plus 13y squared over 2.
Even if 13 over 2 could be reduced, I don't do it in that step.
Okay.
You know what I'm saying? In other words, if that was a 14, I would not figure out the 7. I'm not writing 7 as my first thing. I'm writing 14y squared over 2. Then I'm reducing the 14 over 2 to be a 7.
Okay.
Okay? Step by step, plug in. This stuff is simple if you just follow the methodology and repeat. Okay? Now, that's the antiderivative, and we want to evaluate that from 0 to 13 halves, and you can see we start with the 13 halves, but you can see what's going to happen when we evaluate it at 0. The whole thing goes to 0, right?
Right.
So really, the only thing we have to do is the first evaluation. So over here in the upper right, I'm going to plug in 13 halves in parentheses, cube it, and add 13 times 13 over 2 times 13 halves squared. It's funny, they keep giving us these same things. Notice that 13 over 2 times 13 halves squared is the same as 13 halves cubed. So
yeah.
Let's come up with this number in a calculator. Not a decimal. Cube 13 and put it over 8. Give me that number.
Okay. So 13 cubed is 2,197.
And the 2 cubed is 8, so. And that now tells us what this other is. Because that's this right here. That's 13 over 2 cubed, right?
Right.
So that's 2197 over 8. Now, notice, I'm just going to do this just because I noticed it. I got minus 2/3 of that fraction plus that whole fraction. Well, isn't that 1/3 of that fraction?
Mm-hmm.
There's our answer. 2197 over 24. First of all, make sure you saw what I did. In other words, I basically had minus 2/3 of a number plus a number.
Mm-hmm.
That combines to 1/3 x.
Okay.
And my number in this case is 2197 over 8. So it's 1/3 of that, which is 2197 over 24. And this number here adds to 9, so it's divisible by 9, but 24 isn't. However, if that's divisible by 9, it's also divisible by 3, so I can definitely simplify this. Let's see, if I divide the top by 3, I normally leave the arithmetic to you, but I don't want you to put that in as your answer. It's 7, that's not divisible by 3. Why did I think it was divisible by 3? Let's see, the digits add to 19. Oh, and 1 and 9 add to 10. They don't add to 9. For a number to be divisible by 9, the digits have to add up to 9.
Oh, wow.
Take 72. 72 is divisible by 8. Oh, excuse me, by 9. 7 plus 2 equals 9. Take 108 is divisible by 9. 1 plus 0 plus 8 adds to 9. Any number that is divisible by 9, all of the digits add up to 9. Now notice these added up to 19, which you add again, those add up to 10. 1 and 9 add up to 10. So this might be simplified. I can't think of what might divide into the numerator that would also divide into the denominator. Probably not 24. So I don't know. Even if that wasn't simplified, you might get credit by putting that answer in. Do that in your calculator real quick just to see if that's a whole number or a nice even number, you know, without a string of decimals after it.
Yeah, it has a string of decimals.
So then you want to put it in like this.
Okay.
Okay. All right. Okay, let me blow this up a little bit. Whoops, not that much. Sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y. Draw a typical approximating rectangle. This is not multiple choice, right?
Yeah, it is multiple choice. And then we have to find the region that's enclosed.
Okay, so one of these 4 curves is the way we should do it. Are we going to integrate along the x-axis or the y-axis?
Y-axis.
Yeah, because notice the functions. They're both functions of y. In other words, we don't have a y equal x's. We got x equal y's. So it's definitely going to be a vertical integration because both of our curves are these kind of curves that we see. So this one looks like a candidate. I'm trying to figure out how we're supposed to figure it out. Sketch the region enclosed by the given curves. Okay. If I look at, hold on a second, let me pull up my pen. So I know it's either this first one here or the fourth one, because the other 2 are vertically. In other words, the other 2 are being integrated along the x-axis. Now, the question is which one? Well, what's the x-intercept in these functions? Both of
them. 5.
Okay. There's 5 right there. There's the plus 5. There's the minus 5. If I look down at this curve on the lower right, what are my x-intercepts? They're not 5.
Yeah.
So that's not the one we want. This is the only one that's going to satisfy our problem. Okay. Now, tell me what the integral is going to look like. The function on the right minus the function on the left. Which function is that one right there?
That is, the second one, so 5y squared minus 5.
Oh, notice that that's a parabola that opens left, correct?
Uh-huh.
Here, let me erase my big circle. I don't need that anymore. This parabola that I've drawn opens to the left. That means it's got to have a minus sign in front of the y squared, and that's minus 5y squared, and it also has an x-intercept of 5. So that is that function.
Okay.
And the other one is the other function. It's got an x-intercept at minus 5, and it opens to the right. So what's my integral?
So it's 5 minus 5y squared minus parentheses 5y squared minus 5.
Okay. I'm going to change that to a plus 5 and just erase that parentheses. Okay? Now, what's that become?
So then that becomes...
We know those all don't go to 0 because we can see there's some area there. All right? So if you're tempted to take a quick look at that and say everything cancels, we can tell that that's not true just by looking at it. It's got to have a positive area.
Right.
So combine all these. What do we get?
Oh, it's negative 10y squared plus 10.
Now, we're integrating from what to what?
So it's it
Might be easier for you to see if I erase that. Okay. Now we're integrating from what?
So it's on the y-axis, right?
Yep. Always go from bottom to top.
Okay. Oh, so negative 1 to 1.
Now, over here on the left, give me the antiderivatives of this.
So it's negative 10y cubed over 3 plus 10y.
Evaluated from negative 1 to 1. Now, that sure looks symmetrical to me, doesn't it to you?
Uh-huh.
So let's try my little experiment. Because if I go from negative 1 to 1, I'm going to have to evaluate at both of those numbers. Right?
Uh-huh.
So let's go from 0 to 1 and multiply the answer by 2.
Okay.
Okay, notice how that's going to make it easier?
We
don't have to do the lower evaluation. In other words, when we go from 0 to 1, that lower evaluation, both these terms go away. So the only thing I have is 2 times, and now just plug in. Don't do any simplification first go around. Tell me what to write.
So negative 10 over 3, or 1 cubed over 3.
I would even go that far to write it like that.
Okay.
Plus 3 times 1.
Yeah.
Now you can simplify it. Well, that's minus 20 thirds plus 20. And 20 is 60 thirds.
Mm-hmm.
So I got minus 20 thirds plus 60 thirds. I got 40 thirds is the area. And I included multiplying by 2.
Okay.
So that's what you can put into the answer. And that little trick, your teacher might not even use that on here because, for one thing, I haven't proved that there's symmetry. Although, if you look at the functions, they certainly have to be symmetrical, especially when they visually look symmetrical. And what I need is symmetry about the y-axis. In other words, is this area right there exactly the same as this area right here? And they certainly look symmetrical, and notice the functions are just reverses of one another, so how can they not be symmetrical?
Right.
So I am pretty sure that symmetry is a valid option to use to do that. When they say sketch the region enclosed by the given curves, what do they want us to do? They've already done it. Oh, we're selecting one of the 4.
Yeah.
No, sorry. Let's do that first. Which one represents this picture?
So it's on the y. Is it?
Function of y, which means we're probably not looking at functions. We're probably looking at these parabolas on their sides, right? Both of these are parabolas. That's 8y squared. That's 2 plus 6y squared. So it's definitely one of these 2 lower pictures. Both of which look pretty similar. In other words, that goes through 2, that goes through 2, that's 0, that's 0. So distinguishing which one of these is correct requires us to figure out what that intersection point is right there. We can see that they intersect on this curve at about 8. Over here, they intersect at about 2 and change. So let's go back up and solve for the intersection points. How do you do that? I've got 2 functions here, and I want to know where they intersect. What do you typically...
Set them equal?
Yeah, that's always the way you find how functions intersect, is by setting them equal to one another. So I'm going to take 8, let me work in black, I can't stand that red, it's too thin. 8y squared equals 2 plus 6y squared. Well, if you solve that, you get 2y squared equals 2, y squared equals 1, y equals plus or minus 1 is where they're going to intersect. Well, let's look at those 2. Notice that intersection point comes where y is equal to 1, and on the lower half it's where y equals minus 1. Okay. I solved for the y value of the intersection, not the x. That's why I'm looking at the y scale here.
Oh, okay.
Okay. In other words, it's that value there that I solved for. That is not the same. Over here, that's 0.5. So this is our curve, the lower left one.
Okay.
Okay.
Yes.
Now, the lower left curve, tell me which function is this function? The one on the right.
Let's see. That is the 2 plus 6y squared.
2 is your key right there because there's that 2 right there. And this one doesn't have anything, so that thing's got to have its vertex at the origin. That one there. So that's got to be that curve, the one on the left. So the integral is going to be what?
It is.
Again, hold on a minute. Let me take a look at this thing and see if we got symmetry here. Do we have symmetry?
It looks, yeah.
Yeah, for sure. I mean, not for sure. I wouldn't stake my life on it, but close. I would almost stake my life on it. Hold on. I don't want to cover that up. Okay. So we've got symmetry, which means we can use that little trick, which is kind of a helpful trick.
Mm-hmm.
So I'm going to take the integral of the one on the right minus the one on the left. I don't need parentheses because there's only one term there. dy, and I can certainly add parentheses there. And I'm going to go from 0 to 1, multiplying that by 2, using principle of symmetry. Okay, so now we got 2 times the integral from 0 to 1 of minus 2y squared plus 2. So let's take that antiderivative. What do we get up here on the upper right? I'm going to write it. What's the antiderivative?
Oh, it's negative 2y cubed over 3 plus 2y.
And that is to be evaluated. Almost need a double set of parentheses here. I don't want that 2 to be problematic. In other words, I almost prefer to take this 2 and set it aside, do the whole problem, whatever I come up with, multiply it by 2. The problem with that is you frequently forget to do that last step.
Right.
So to avoid making that mistake, I'm going to carry it forth every row. Okay? And the next thing, again, I don't have to evaluate at 0, so I only have to evaluate it at 1. So it's 2 times 1 cubed over 3 plus 2. So now we've got 2 times minus 2/3 plus 2. Well, minus 2/3 plus 2 is 4/3. Times 2 is 8/3. There's the area. All right. These are fun. Actually, I honestly believe that area between curves is one of the easier parts of calculus.
Yeah, I was just thinking that it's a lot less intimidating.
Yeah, there's
walking through that.
Nothing really to understand. It's just working through and figuring out which curve's on the right and which picture works. I'm going to have to shrink that momentarily just to figure out which. Oh man, the problem is when I shrink it, I can just barely see it. Well, let's look at our functions. We've got 3 functions here. They're all y functions. Y is functions of x. So what's the most likely axis we're going to integrate on?
Y.
No, remember?
Or I mean x, sorry.
The x. In other words, we're going to have a dx after our integral sign because all of our functions are going to have x's in them, not y's. Okay. Now, here's the way we're going to do this. Now, let's see. Hold on a second. How can we easily figure out which function, which picture is correct? Let me go back. I can't get the whole thing on this page. Oh, yes, I can. Yeah, I can. Just Not really. Let me have a look at these two bottom ones here. Well, we got a vertical line in there, right?
Mm-hmm.
At different areas. In other words, the vertical line here is x equal 2. Here it's x equal a half. Down here it's x equal 1.5. And over here it's x equal 0.1. So from that alone, we should be able to figure out which function. I don't see a vertical line. Ah, my mistake. That vertical line is not part of the functions. That vertical line is an assistance on how we're going to do this problem. First of all, we've got to figure out which picture we're looking at. Let me see if I can figure out an easy way to do it. Let's see, that's 12x, so the steep line has to be 12. Well, the rise is 6 over the run of 2. That slope is not 12. That's not it. Number 1, the one I'm pointing at. That's not it. This one over here, we go up 6 over a half. That's a slope of 12. So that dotted line on the left could easily be that middle function. And this function is 1/3 slope. Well, how do I get 1/3 slope? I go up to 1 over 3. So this bottom dotted line that I'm pointing at is this third function. Now the only question is the curved line this function over here? Well, I believe it is because of, let me get it on here so I can write. In other words, we know that line is correct. We know that line is correct. Is the dotted line the proper dotted line? Well, the thing to figure out is where it intersects with the 12x. In other words, does 12x, we know the other function is 3 over x. Question is, does that intersect at x equal 1/2? Well, let's do the math. 12x squared equals 3. That means x squared equals 1/4. That means x equals plus or minus 1/2. So this curve right here that intersects at x equal 1/2 is the only curve that does that.
Mm-hmm.
If I go back down here, notice that that intersection on the lower right is not 1/2. This intersection on the lower left is not 1/2. And I'm looking for the intersection of that point right there.
Okay.
X value of it. Well, when I solved the two equations, I got x equal 1/2. This is the only one that fits.
Mm-hmm.
So the upper right is the one they're talking about.
Okay.
Okay, so now let me take a picture of that so I can use my drawing pen. And let's figure out how we're going to do this. Notice that there's no single function that's above the lower function for the whole time.
Mm-hmm.
So I got to do it in steps. I got to do the integral of the function on the left minus the function on the bottom from 0 to 1/2. Well, the function on the top is 12x. See why? Function on the bottom is 1/3 x. In other words, there's the top function. There's the bottom function. And this integral here, integrating from 0 to 1/2, is going to give me this area right here. You with me?
Okay. Uh-huh.
And I'm going to add to that this area, which is the function on the top, the integral. Well, that's this function here, the curved function. That's 3 over x minus the function on the bottom, which is still 1/3 x. Only this one, I'm going to go from 1/2 to whatever that intersection point is. Well, let's just assume it's 3. And let's see, where would 3 over x be equal to 1/3 x? Multiply both sides by, I get 9 equals x squared. So yeah, x is 3. So this one I'm going to go from 1/2 to 3. Okay? So this is the setup. In other words, I've got the integral of that, which is the area to the left of the vertical line, plus the integral of that, which is the area to the right of the vertical line.
Okay. That makes sense.
That's why they stick the vertical line in there as a tip as to how to do this problem. In other words, you cannot do this problem with one integral. You got to have 2 different integrals with different limits of integration.
Okay.
Okay? And we could solve this. Would you rather solve this or go to another one?
Maybe just solve this. So I bet
Okay? Let's do it. Let's start at the top. I'm going to do the top over here on the left. Tell me what the antiderivative of each term is.
all right, so that's 12x squared over 2.
Okay? 12x squared over 2 minus 1/3 what?
X squared over 2.
No, just, oh, excuse me, yeah. So let's simplify that. That becomes 6x squared minus x squared over 6. And I'm going to evaluate that from 0 to 1/2. That's pretty easy. Let's go ahead and come up with that number. Because I don't have to do the bottom, because it's 0. So this will be an easier one to evaluate than the next one, because the next one's got a lower limit of 1/2, and I am going to have to evaluate both ends of that. But this one's relatively easy. So I got what?
6 minus 1/6.
Hold on. Plug in 1/2 for x.
Oh, 1/2. I don't know why I was doing 1.
Well, because everything we've been doing has had 1 in it.
Yeah. Oh, okay, 1/2. So then it's 3 minus...
Hold on. 1/2 squared is 1/4. So that becomes 6 fourths, which is 3/2, minus 1 over 24. So this becomes 36/24 minus 1/24, 35. This is equal to 35 over 24. So this area right there is 35 over 24.
Okay.
Now let's do the second one. Now let me erase so I have writing room. We don't need to see what we did on the first one. We've already written the answer. Now let's integrate this one. What's the antiderivative?
So the antiderivative is...
Make it a negative exponent is the secret there.
Okay.
That's the same as 3x to the minus 1.
Okay.
Ooh, that gives problems, doesn't it? Because now if it's 3x to the minus 1, and I add 1, I got 3x to the 0 divided by 0. That can't be right.
Mm-hmm.
This is the one special case where you cannot use the power rule.
Oh, okay.
Not use the power rule when you got x to the minus 1. The integral of that is 3 times the natural log of x. In other words, the integral of 1 over x is the natural log of the absolute value of x. That's what it is.
Okay.
Can't use the power rule. You got to use that knowledge. The knowledge that the integral, the antiderivative of 1 over x is natural log of x. So, we've got 3 natural log absolute value of x, that's the antiderivative of that part, minus 1/3 x squared over 2, turning that into a 6. Now we're getting echo. I can live with the echo. Can you hear me?
You're kind of cutting out a little bit.
Okay, we only got 4 minutes. So I hate having you not going to work. Let me just talk. Try to gather what.
Okay.
So I'm going to evaluate from 1/2 to 3. So what is that? That is 3 natural log of 3 minus 1/6 times 3 squared, which is 9. So it's that quantity minus 3 natural log of 1/2. Take away the absolute value because these are both positive numbers. Don't need the absolute value anymore. Minus 1/6 of 1/2 squared, which is 1/4. So that is the area of the second part. Still there, Morgan?
Mm-hmm.
Okay, good. And since we're out of time, I won't go through coming up with an answer for that, but make sure you write it down or something. In other words, you can get that out of a calculator, and you might have to. You're going to have to get natural log of 3 out of a calculator and natural log of 1/2 out of a calculator. But the rest is just algebra, and you can come up with a number. So your total area is going to be 35/24 plus whatever that number is inside that stuff circled on the far left.
Okay.
Fun stuff.
Right.
All right. Morgan, I'm going to let you go, and I'll talk to you next time.
Sounds good. Thank you.
All right. Bye-bye.